Welcome back for the fifth session in a module 5. It is the instance based learning, reinforcement learning, and the evaluating hypothesis. So, in the earlier sessions, we have covered the two chapters, instance based learning, reinforcement learning, and now in this session, we will be looking into the evaluation of the hypothesis. So these are the contents that we are going to check, that is evaluating the hypothesis, the motivation behind this, and there are some key difficulties we have, and the second content is the estimating hypothesis accuracy, and there are some basics of sampling theory we are going to study, and then as a final we will study the binomial distribution. So, empirically evaluating the accuracy of hypothesis is actually a fundamental to the machine learning here. Okay, so the motivation here for evaluating hypothesis is that in many cases it is important to evaluate performance of the learned hypothesis as precisely as possible here. Okay, so one reason we can simply is to understand whether to use the hypothesis or not. Okay, for example, when learning from a limited size databases indicating the effectiveness of different medical treatments, as an example if we take up, it is important to understand as precisely as possible the accuracy of the learned hypothesis. And the second reason is that evaluating hypothesis is actually an integral component of many learning methods. For example, in post pruning the decision trees, in order to avoid the overfitting, we must evaluate the impact of possible pruning steps on the accuracy of the resulting decision tree. So therefore it is important to understand the likely errors inherent in estimating the accuracy of the pruned and the unpruned trees. So because of these reasons, the estimating the accuracy of hypothesis is very important, and it is actually relatively straightforward when data is plentiful. Okay, so however, we must learn a hypothesis and estimate its future accuracy given only a limited set of data. But there are two practical difficulties that might arise in estimating the accuracy here. Is the first one is bias in the estimate. Okay, so the first, actually if you consider the observed accuracy of the learned hypothesis over the training examples is often a poor estimator of its accuracy over the future examples, because the learned hypothesis was actually derived from these examples, and they will typically provide an optimistically biased estimate of the hypothesis accuracy over the future examples. And this is especially likely when the learner considers a very rich hypothesis space, enabling it to overfit the training examples. So when you have that, to obtain an unbiased estimate of future accuracy, we typically test the hypothesis on some of the test training examples which are chosen independently of the training examples and the hypothesis here. And the second, the main difficulty here is the variance in the estimate. Okay, even if the hypothesis accuracy is measured over an unbiased set of the test examples which are independent of the training examples, sometimes the measured accuracy can still vary from the true accuracy. Okay, depending on the makeup of the particular set of training examples. Okay, the actually when you have the smaller set of test examples, the greater the expected variance. Okay, so this that is because of these reasons, evaluating hypothesis or estimating the hypothesis accuracy is very important. Okay, so when evaluating a learned hypothesis, we are most often interested in estimating the accuracy with which it will classify the future instances, right? Okay, at the same time we would like to know the probable error, okay, in this accuracy estimate. For example, probable error in the case says what error bars to associate with this okay, estimate. In this session, we will actually consider the some of the setting for learning the problem. Okay, for example, we say that there is some space of the possible instances, that is, okay, given as x. Okay, for example, assume that set of all people, okay, over which the various target functions may be defined. For example, people who plan to purchase new, okay, new skies this year. We assume that different instances in x may be encountered with different frequencies. A convenient way actually to model this assumption is to assume there is some unknown probability distribution d that defines the probability of encountering each instance in x. For example, so we write d. Okay, this is the probabilistic distribution. Okay, this is a d. Fine. For example, d might assign a higher probability for encountering a to encountering 19-year-old people than 109-year-old people. Okay, and if you notice here, the d says nothing about whether x is a positive or negative example. It only determines the probability that x will be encountered. Okay, when we have this, the learning task is to learn the target concept, or we call it as a target function f, by considering the space h of possible hypotheses. Training examples of the target function f are provided to the learner by a trainer who draws each instance independently according to the distribution d, and then who then forwards the instance x along with its correct target value f of x to the learner. To better understand this, let's consider the target function. For example, people who plan to purchase new skies this year. Given a sample of training data collected by surveying people as they arrive at the ski resort, in this case, the instance space x is the space of all people who might be described by attributes such as their age, occupation, how many times they skied last year, etc. Now, in this case, the distribution d specifies for each person x the probability that x will be encountered happens to be as the next person arriving at the ski resort. Okay, the target function now in this case, that is f x tends to 0, 1, classifies each person according to whether or not they plan to purchase skies this year. With this general setting, we are interested actually in the two questions. Given a hypothesis h and a data sample containing n examples drawn at random according to the distribution d, what is the best estimate of the accuracy of h were the future instances drawn from the same distribution? And the second is what is the probable error in this accuracy estimate? Okay, so in order to answer these questions, we need to understand there are two notations: accuracy, okay, and then the error here. Okay, so for that, let's try to define the sample error. The sample error of a hypothesis with respect to some samples s of instance drawn from x is the fraction of s that it misclassifies. The definition is given as the sample error, which is denoted as error s of h of hypothesis h with respect to the target function f, and data sample s, which is given as this formula. Okay, error of s says it is a sample error, okay, which is given as 1 by n of summation of x belongs to s delta of f of x comma h of x, when n is the number of examples in s and the quantity, this quantity is 1 if f of x is not equal to h of x and 0 otherwise. The true error of a hypothesis is the probability that it will misclassify a single randomly drawn instance from the distribution D. So the definition here is which we denote it as error D. Error S is the sample error, error D is the true error. Okay, so it is denoted as error D of H of hypothesis H with respect to target function F and distribution D, and it is the probability. Okay, so the here if you see here, it is a probability PR of f of x is not equal to h of x. Okay, this notation PR okay, x belong to D, it actually denotes the probability, and okay, is taken over the instance distribution D. Right, so what actually we usually wish to know is the true error of a hypothesis, because this is the error we can expect when applying the hypothesis to future examples. Okay, so all we can measure however is the sample error, okay, of the hypothesis for the data sample S that we happen to have in hand. The main question considered in this session is actually how good an estimate of error D of H is provided by the error of S. Okay, and next okay, to answer the question, that is how good an estimate of error of D of H is provided by error S of is best understood by defining the confidence intervals for discrete valued hypothesis. Okay, so more specifically, suppose we wish to estimate the true error for some discrete valued hypothesis H. So based on its observed sample error over a sample S, okay, where the sample S contains n examples drawn independent of one another and independent of H according to the probability distribution D. Okay, and n is greater than or equal to 30, and hypothesis H commits R errors over these n examples. So that is error of S, that is sample errors of H is equals to R by n. So when you have these conditions, the statistical theory allows us to make the following assertions. First one is, given no other information, the most probable value of error D of H is error S of H. Okay, and second one, with approximately 95% probability, the true error D of H lies in the interval, that is plus or minus 1.96 square root of sample error of H into 1 minus sample error of H divided by n. Okay, so in order to illustrate this, consider an example. Assume that the S contains n is equals to 40 examples and the hypothesis H commits R equals to 12 errors over this data. Now in this case, the sample error, okay, is given as R by n, that is 0.30, and given no other information, true error is error D of H is equals to error of H, that is same as the sample error. Okay, so with the 95% of the okay, with a 95% confidence interval estimate for error D of H, so we can calculate this. Okay, so 1 point plus or it is 0.30, okay, sample errors 0.0 plus or minus 1.96 into 1 minus 0.3, that is 0.07, okay, which is equals to 0.30, which is equals to 0.14. Okay, so this is the confidence interval. Okay, now the above expression is for the 95% of the confidence interval and can be generalized to any desired confidence level. The constant 1.96 is used in case we desire a 95% confidence interval. A different constant, for example Zn, can be used to calculate the n% confidence interval. The general expression for approximate n% confidence interval is written like this. So previously we had taken 1.96. Now in this case, in general, we can write it. Okay, so it is a different constant Zn. Okay, it is for the n% confidence interval. So here we have used 95%, that is why we had taken 1.96. Because if you look at this, okay, interval, for each n% confidence interval, constant has been defined. Since we have assumed it as 95%, we have taken it as 1.96, but it can be generalized like this, Zn. Okay, so this is a sample example on the uh, uh, okay, confidence intervals. And one more example that we can use here is, for example, S contains okay, n as 40 examples, okay, and with the 68% confidence interval. So if you see here, 68% confidence interval, we have the value of Zn as 1. So you can substitute this value and you can get the value, right? So now let's try to understand some of the basics of sampling theory. Okay, that is, let's introduce the error estimation and the estimating binomial properties. So precisely, how does the derivation between sample error and the true error actually depends on the size of the data sample. In this question is an instance of a well studied problem in case of the statistics, that is the problem of estimating the proportion of a population that exhibits some property given the observed proportion over some random sample of the population. In our case, the property of interest is that H misclassifies the example. So now the key answer to answer this question is to note that when we measure the sample error, we are performing an experiment with a random outcome. First, we collect a random sample S of n independently drawn instances from the distribution D, and then measure the sample error, okay, that is error S of H. So as it is noted in the previous section, if we were to repeat this experiment many times, each time drawing a different random sample Si of size n, we would expect to observe different values for the various error Si of H depending on random differences in the makeup of the various Si. Okay, so we say in such cases that error Si of H, the outcome of the ith such experiment, is actually a random variable. In general, one can think of a random variable as the name of an experiment with the random outcome. Okay, and imagine that we were to run k such random experiments measuring the random variable, that is error S1 of H, error S2 of H, until error Sk of H. Imagine further that we then plotted a histogram. Okay, so if you see here, so this is the histogram. Okay, histogram displaying the frequency with which we observed each possible error value. As we allowed k to grow, the histogram would approach the form of the distribution. So this table actually, this diagram, okay, it is called as the binomial distribution table. Okay, so let's try to understand now the binomial distribution. So actually, in order to understand the binomial distribution is to consider the one problem here. For example, you are given a worn and bent coin and asked to estimate the probability that the coin will turn up heads when it is tossed. Let us call this unknown probability of heads P. You toss the coin n times and record the number of times r that it turns up heads. A reasonable estimate of P is now r by n. Okay, note that if the experiment were rerun generating a new set of n coin tosses, we might expect the number of heads r to be vary somewhat from the value measured in the first experiment and yielding to somewhat different estimate for p. Okay, now for this problem the binomial distribution describes for each possible value of r, that is from 0 to n, the probability of observing exactly r heads given a sample of n independent tosses of a coin whose true probability of heads is p. Okay, uh, so when you have this, okay, the estimating p from a random sample of a coin tosses is equivalent to estimating the error d of h from testing h. Okay, so the probability p that single random coin toss will turn up heads corresponds to the probability that a single instance drawn at random will be misclassified. The number r of heads observed over a sample of n coin tosses corresponds to the number of misclassifications observed over n randomly drawn instances. So thus r of n corresponds to r by n corresponds to error of h. Okay, that is the sample error. The problem of estimating p for coins is identical to the problem of estimating the true error for the hypothesis. The binomial distribution actually gives us the general form of the probability distribution for the random variable r, whether it represents the number of heads, okay, whether it represents the number of heads in n coin tosses or the number of hypothesis errors in a sample of n examples. The detailed form of the binomial distribution depends on the specific sample size n and the specific probability p or the true error on the h. Okay, the general setting to which the binomial distribution applies is there is a base or underlying experiment, for example tossing a coin whose outcome can be described by a random variable, say y. Okay, now the random variable y can take on two possible values. Okay, for example, if while tossing a coin, if it is head we say y equals to 1, and if it fails we say it is y equals to 0. Okay, the probability that y is equals to 1 on any single trial of the underlying experiment is given by some constant like p independent of outcome of any other experiment. The probability that y equals to 0, okay, is therefore we say it is 1 minus p. So typically p is not known in advance and the problem is to estimate it. Okay, and the series of n independent trials of the underlying experiments is produced. For example, n independent coin tosses producing the sequence of independent identically distributed random variables y1, y2 and yn, and this can be we can use r in order to denote the number of trials for which yi is equals to 1 in series of the experiments. So this is what is the formula that can be used. And the fourth is that the probability that the random variable r will take on a specific value r. For example, the probability of observing exactly r heads is given by the binomial distribution. So this is a formula for binomial distribution. That is the probability of r equals to r is given by n factorial divided by r factorial into n minus r factorial p to the power r into 1 minus p of to the power n minus r. Okay, so the binomial distribution characterizes the probability of observing r heads from n coin flip experiments as well as the probability of observing r errors in a data sample containing n randomly drawn instances. Okay, so these are some of the hypothesis, evaluating hypothesis, that is binomial distribution, which comes under the basic sample theorem. For that we have understood what is the sample error and the true error. So this is the end of a session. Thank you.